Welcome everyone to this new colloquium. And today's speaker is Daniela Calvetti from Case Western Reserve University. I'll introduce her in Italian, leaving the floor to her. Daniela Calvetti ha conseguito il dottorato in matematica presso la University of North Carolina a Chapel Hill nel 1989. In seguito ha ricoperto posizioni presso varie università statunitensi e dal 1997 è docente presso la Case Western Reserve University, dove è attualmente titolare della cattedra James Wood Williamson Professor of Mathematics, Applied Mathematics and Statistics. L'attività di ricerca della professoressa Calvetti copre numerosi ambiti dell'analisi numerica e della matematica applicata, integrando strumenti provenienti dalla probabilità. Il suo lavoro ha importanti applicazioni anche in altri settori scientifici come la medicina e le neuroscienze, per le quali ha sviluppato diversi modelli predittivi. È particolarmente nota per i suoi contributi all'algebra lineare numerica e alla risoluzione numerica di problemi inversi, con un'enfasi su approcci bayesiani e sulla scienza dei dati. È autrice di oltre un centinaio di articoli scientifici, oltre a varie monografie su diversi aspetti della matematica computazionale. È stata inoltre eletta Fellow della Society for Industrial and Applied Mathematics, SIAM, nella classe 2023, in virtù dei suoi contributi alla Numerical Linear Algebra based in Scientific Computing and Inverse Problems and Applications. And today she'll talk about linear algebra joins probability in the search for sparse and group sparse solutions with few data. And thank you for accepting our invitation.
Okay. Thank you for having me. Thank you for the invitation. I can do it both either in Italian or English. Is there somebody here who does not speak Italian? Good. So we'll do it in English. Makes it easier. Okay. So yeah. So this is. I'm going to go over an easy, introductive way of showing how mathematics is wide, and there isn't a single area that lives on its own, and how linear algebra in particular really pops up everywhere. So this is work at bridging linear algebra and probability is what has occupied me for the past 20 years, and somebody always says that every problem that I work on, in the end, it always ends up being a numerical linear algebra problem. And it's true. So please interrupt me if I'm not clear. I will try to sort of give a very approachable introduction to the subject. So basically what I've been looking at for the past, this is not 20 years, it's more like close to 40, is inverse problems. And inverse problems are inverse because it means that there is a forward problem. Forward problem is pretty much follows the natural flow of causality. There is an input, there is a model, I would call it a forward map here, and there is an effect. So you can compute the effects of a cause. The inverse problem is the reverse. So I step on the scale today, and if my weight is 52 kilos, okay, then this is a direct problem. If I give you 52 kilos and you have to get back to the person who weighs 52 kilos, is a little bit different, right? It's not as straightforward. And, but, this is not as, this is not as simple as this. A lot of the problems that, a lot of the technology that we rely on really today, the motor is an inverse problem. Every non-invasive diagnostic is effectively an inverse problem. So these are very important and usually very difficult. There is some sort of conservation of, I guess, forgiveness here, because the more forgiving the forward problem is, the more difficult the inverse problem is. Meaning that if the forward problem really kind of like smooths out the details, and it can take some variations, some perturbations, then the inverse problem is going to be very difficult because the effect that we are measuring, that we're looking at, is already smoothed out. It's pretty much hiding often the traits of interest of the input that we're trying to recover. So there are many challenges in inverse problems. And what I've done here is I've been biased on the type of challenges that I encounter most in the type of application that I'm looking at. One challenge is that the data tend to be few and noisy. Think about X-ray. You can go and they can take a very accurate X-ray of your body, and then you walk home glowing. So the number of, say, the amount of ionizing radiation that one can use for diagnostic has to be limited. And noisy because many of these measurements are done with equipment that is not fully accurate. It's done on living or moving objects, and therefore, in addition to what we would like to measure, there is, or the effect, let's say, that we would like to measure of the unknown causes that we're trying to recover, there is also modeling error, there is, let's say, noise error, there is inaccuracy of the instrumentation. So that's what the few and noisy stands for here. Now, second bullet here. In many cases, we need real-time solutions. So, for example, if you're trying to do weather prediction, or if you're trying to predict whether a river will break the banks, you want to do it in real time. You want to make, you want a solution to be computed before the event is observed. So if you have an inverse problem, which is part of a real-time problem, often it has to be solved fast. Often you have to trade speed for accuracy. But ideally, you would like to have both. And now, in addition, there are many applications where the solution that we're looking for have traits, meaning that you may not think that you're looking for a particular solution until somebody shows you a solution which is totally off the wall. For example, you have a bug program, you put an output and it's all over the place. Then you know that is not what you wanted. So many solutions that we want are sparse. They can have sparse representations, or they are sparse in blocks. Examples of this, you're looking for, well, the typical is if you're looking for stars in a night sky.
I concentrate cows from the first grade, no?
Yeah.
So, sparse in the sense that you...
Sparse
there is also some physical...
So, sparse means that you expect that the solution is probably going to be in the next slide. Let me try. Okay, no, it's the next. So, it means sparse means that we're looking for a solution that for most of the entries are 0, and there are a few entries, so the support of the solution is concentrated on a very small. What does it mean? Sometimes you simply, I work a lot on brain, and the brain is never active, all of the brain at the same time. There are only small parts of the brain which are activated. So physically, effectively, yes. So this is an expert knowledge. If you're an investor, right, if you're trying to invest your money and you want to buy stocks, you don't want to buy a stock in every packet because you're going to pay entry fees and exit fees. So you want to have block sparsity. You want to concentrate, or you don't want to buy stocks from, just anything. So sparse, you're right, sparse is in the eyes of the beholder, I guess. But, okay, so, we're at the next slide here. So classical inverse problems, classical forward problems are what is called well-posed, whereby well-posedness, it means that we have a solution, the solution is unique, the solution changes continuously with perturbations in the data. We take off the glasses and we think of this with a grain of salt because numerically, some of this may not be strictly. Now, what is an ill-posed problem? A problem that is not well-posed. So, inverse problems by their own nature, think about the 52 kilos, right? By their own nature, they're often ill-posed. Many of the inverse problems that I look at do not have a unique solution, if they have a solution. And in many cases, in particular when the forward problem is forgiving, the inverse problems is difficult to solve in the sense that if you make a small perturbation to the data, that results in a very large, let's say, amplification of that perturbation in the solution. Excuse me. Okay, so now we're going to just look at linear inverse problems, try to put together linear algebra and probability in the quest for looking for a solution of this problem here. So I have an observation. So this is the effect that I'm measuring, B. I think I'm measuring B. I think that B is given by a forward operator, A, applied to the input, which is what I want to recover, X, and then there is some error, which for now I'm thinking that is additive here. And this is linear, so A is a matrix here, and I'm thinking that I have few data, so M is less than N. Excuse me. So, that's when the probability entered in my life, and that was about 22, 23 years ago. So the data are too few, they are insufficient, they're not all that good, but we take them because that's the best that we have. We have a matrix A here that has a non-trivial null space, effectively, so many of the problems are highly underdetermined. So what we need to do to have, any hope of coming up with a meaningful solution is to actually supplement the data with additional information, with additional. So, in many cases, if you talk with people from application, they will be able to describe to you what they want in English or Italian, in the language of their discipline, but not always they can translate the features that they expect to have in the solution in quantitative terms. And that's where that moment comes. That's a moment to stop, start thinking, and see what we can do. And that's where the mathematician puts the formulas away and behind the screen, in the back of the brain, start thinking about how to translate qualitative traits into quantitative terms that can be used. So, and that's where the probability comes in. Because probabilistic framework, they are better, they are more nimble at making qualitative and describing qualitative information about the solution. They're not going to describe it in terms of numbers, they're going to describe it in terms of functions, probability functions. Then, these days, it's also very important to have what is called margins of error or quantification of the uncertainty, because the solutions that we present is maybe one instance of a solution, but we would like to know how much we can trust. So they're also very good at quantifying uncertainty in the solution. And this was, this has been into action for a long time. Probabilistic framework has been around for 50, 60 years. The problem with making it work is that it was missing state-of-the-art numerical analysis to make this probabilistic methods actually usable in practical problems. So let's go ahead and let's see how we put together probability, inverse problems, and linear algebra in the search for sparse solution of underdetermined problems. Okay, so sparse, now I'm coming to the question that was asked before. So in general, if one looks for a definition of what sparse means, and by the way, sparsity requires a parameterization, meaning that when I say that something is sparse, I'm saying that X is sparse. I mean that most of the entries of X are 0 here. Now, if I change my parameterization, this can change. So I can have sparsity, I can have quality like sparsity in a signal that is not sparse if I start representing it in terms, for example, of Fourier components or wavelet components. So there is always a moment in which we have to think about how we represent our quantity, and if we want to use the tools of sparsity, maybe we have a way of obtaining a sparse representation on which we can hook all of the machinery that has been developed. So sparse representation often, at least in many of my applications, is obtained by taking a matrix here. This is a matrix L, which is K by N. N is the dimension of X here. And I apply L to my original unknown X, and I get Z. Z is L times X. And now what I want to say is that Z is sparse. So I'm putting the sparsity. The sparsity could be directly on X, or it could be on a representation of X via a sparsifying transformation L. And I will have an example of this. Typically, we have that the number of measurements is less than the number of unknowns, which is less than, let's say, the number of new unknowns. So Z will be a vector which has more components than X, which has more components than the measurement. So if you wish, by going through this transformation here, I'm making my problem even more underdetermined. So often say, well, how can we hope for really 0 here? So most of the time we trade sparsity for what we call compressibility, meaning that we think that is enough for the entries of Z or X to be below a certain threshold to be considered 0. So that's, now, there is a long tradition of looking for sparse solution methods that promote sparsity. So it goes back to Donohoe. There was Mike Saunders who's worked on it. And then in 2007, I call 2007 the year of L1 sparsity. And that's Candace, Romberg, and Tao. They came up with, some papers, some important papers, in which pretty much they were promoting and they were demonstrating how you can penalize, so you can make the solution X pay a penalty for growth in the one norm, and in that manner you automatically promote sparsity in the solution X. And that's because if you think about the classic ball in the different norm, well, the one sorry, I promise I will not rule. The one norm meets. And in fact, you could have a norm which is less than 1, but then we get into problems that we don't want to discuss today. Okay. I'm simple person when I talk to, when I want to be simple when I think about this problem, and I like to be consistent. And it's not that I don't like different norms, but it's kind of like I'm a little bit disturbed because there is a 2 norm here, and there is a 1 norm here, and sometimes there is a 1 norm and a 2 norm, and it's like, why can't you do everything in the 2 norm, which is kind of like the intuitive norm. The Euclidean norm is what we experience like every day. So, introduction to the Bayesian framework here. And that's what we will be able to do in the probabilistic setting, is to not change norm and at the same time come up with a method which promotes sparsity. So every unknown, so this is the mantra, Bayesian mantra here. Every unknown parameters are modeled as random variables. I should not be there. This is a brand new talk, by the way. So random variables are described in probabilistic terms, so they are described by density functions. And in our case, in our context, we have noise that we don't know, and we have the unknown that we don't know. So we have 2 natural candidates for random variables here. Also, we like to think about linear problems. Linearization is a tool that is used very extensively here. In the equivalent of linearization in probability is Gaussianity. So Gaussian densities are preferred because they are really easy to work, they are studied, they can be described fully with the mean and the covariance here. So we try to stay as Gaussian as possible. So now we're assuming that the measurement noise, so the plus epsilon that I had, is white Gaussian, meaning that has a mean 0 and there's a standard deviation, or a covariance which is an identity. Now, this is not restrictive in the sense that you could have other covariance matrices as long as this is a proper Gaussian, because the covariance is symmetric, positive, definite, and you can do what is called the whitening. So you do a transformation, you transform everything, and you come up with this standard problem here. Now, if we know x, then this probability density function, this distribution here, would tell us how B would give a distribution of B. It's actually pretty wrong. The likelihood that we see B, dx. So next, let's go ahead and we want to express the sparsity of x or z in terms of probability densities that they have to reflect what is our intuitive. Doesn't look very intuitive, this slide here, but it's more intuitive than it seems. Intuitive idea of sparsity. What does it mean that a vector z is sparse? It means that most of its entries should be close to 0. But I don't know the entries, so they're random variables. I don't want to, be too far from Gaussian. So let's assume that I describe them with Gaussian distributions. If I want to be sparse, if I want z to be sparse, it means that most of the entries should be 0, but not all of them will be 0. There will be some that are different from 0. But those which are different from 0 should be independent of the ones which are close to 0. Because otherwise, if I'm linked to my neighbors, I'm going to have a problem jumping up suddenly. So, this justifies this assumption here that the entries of Z are mutually independent entries. They are normally distributed. They are 0 mean because in the end we expect most of them to be 0. So the expected value is 0. And they have a certain variance here, which I denote by theta j. So right now we're shifting everything to the variance. The problem is on the variance because the mean is the same for everyone. So what do we say with this variance here? And let me hope. I'm going to go to this picture here rather than the formula. So think about this signal here. It's mostly, right, mostly 0. And then we have a few entries which are definitely different from 0. And I want to describe something of this type in probabilistic terms. So, color coding here. Think about the red points here. This component here, if I want to describe it with some Gaussian, I will take a Gaussian, a zero mean Gaussian here, and I will take the standard deviation, which tells me how far the signal is likely to stray away from the mean, to be very small, because that will keep it close to where I expect it to be. Now, let's look at, these are blue. Let's look at these blue dots here. These are significantly away from 0. But I'm still describing them in terms of zero mean Gaussian, the way in which essentially convey the fact that in these positions here, in some positions, I could have values, realizations which are very far from 0, is by giving the Gaussian, zero mean Gaussian, a large standard deviation. The larger the standard deviation, let's say the more likely, the more probable it is that I will get values that are away from the mean. So, now, there is a little problem, and is that the rule of the game is that you don't know the support of the solution, because if you knew where these points here are, what would you do? You would just say everything else is equal to 0, we set the remaining, right, of the solution equal to 0, and then we just solve the problem for this much smaller number of unknowns. So, I don't know which one of these entries here have small or large variances here, which means that the variance is another unknown. And if the variance is an unknown, then it has to be modeled, base, right? It has to be modeled as a random variable. So now, I'm doubling the number of random variables. Like, looks like one of those, games in the streets with the cards and everything. So I'm now doubling the number of the random variables. I'm also doubling the number of objects that I need to describe in terms of probability density. So now I need to come up with some probability density function to describe typical, what I expect of these variances here. And this has to be the status. I'll call them status, the variances, and the status have to be positive. They also, most of the time, we expect them to be fairly close to 0. The closer, the sparser, the more of them close to 0 they will be. But some of them should be naturally coming out far away from 0 to reflect the fact that we have some action here. So, there are many probability distributions, probability density functions that would do the job among the many possible choices for the past almost 20 years. What we've done is we have described the status, the variances using gamma distributions. And now you see this is a plot, right, of a gamma distribution, what it looks like. And now, back a second, let me go back here. And in fact, if one wants, one can actually generalize this and describe the variances in terms of a generalized gamma distribution. The variances also should be mutually independent, because I don't want to undo with the variances what I did with the independence of the components. Right? If I make the variances dependent, then let's say, the jumping will be constrained by the neighbors. So all of the variances and all of the unknowns are mutually independent. This is the expression for a generalized gamma. For the gamma you put r equals to 1 here. And this depends on parameters, shape parameter and scale parameter. And there are ways actually to set them to address particular problems here. Now, I need to describe right now my prior, which is what I know about the unknown that I'm trying to estimate a priori before I've looked at the data. So I'm using the law of total probability here. So the joint prior of z and theta is going to be given by the conditional prior of z given theta times the prior for theta, which I call hyperprior because it's like at another level, at a higher level here. And by the way, this one we said was going to be Gaussian, right? Conditionally Gaussian. And so now you can see, if you have a forward computing mind, you can see that the choice of this expression here, does well, goes well together with the conditionally Gaussian. So this is what we did. Now we need to put the likelihood. We have the likelihood described. That's where the data comes in, and that's what is going to decide which one of these unknowns will be set to 0, will stay put to 0, and where the action will be. So the data at some point will decide what is the support, the real support of the solution here. So if the sparsity is for z, think in terms of wavelet transform, Fourier transform, increments for solution, which is often how we use the sparsity in applications here. Then we are expressing the sparsity via the sparsifying transformation L here. And we had originally the likelihood written in terms of x, but now I need to mesh, I need to have coherence between the prior, the expression of the prior, which is for z and theta, and the likelihood. So what I do here is I make this change of variables. So this is how I go back to x from z via the pseudo inverse of L, and I get my likelihood here. So I'm assuming that L is full rank and that z has to be in the range of L. Now, Reverend Bayes, right? Reverend Bayes didn't say anything. He was talking about miracles, and but you know, the theory, Bayesian theory, puts together the likelihood and the posterior, the likelihood and the prior, and gives us the posterior, which is how. Let's try to read this in words rather than in formulas here. This expression here is telling us what we can say about the unknown z of interest and the parameters theta, the variances we have to, given the data conditioned on the data that we have observed. So you change the data, you change the observation, we may come up with a different conclusion. So it depends on the data, but it also depends on, the data, but it also depends on what we a priori, so we are putting additional information here. That's why Bayesian probability is also sometimes called subjective probability. We're also putting some, let's say, expert qualification about the solution via the prior. So we're putting together the likelihood and this part here, which comes from the prior. You can see the conditionally Gaussian portion, And now I've done some color coding here to make it a little bit easier to follow, because this part here, this expression here, it was in the previous part. It contains logarithm, it contains summation, but what is important is that it only depends on theta, it doesn't depend on z. So now we have broken up this posterior density, which, if we were probabilists, if we were in the Bayesian inverse problems people, that would be the end of the story, that would be our solution. But, we want to compute something here. So this depends only on theta, this depends only on z, and now this is the glue. This term here depends on z and theta here. And what we want to do, what I want to do is I want to go ahead and I want to compute, I want to exhibit a typical or a solution that represents what I found from my data and my prior and the observation model here. So I'm computing, and this is fairly common, to represent, to give a a single point estimate of a probability density via the maximum a posteriori estimate, which is to say computing the realization of z and theta, which are most likely to realize themselves in the posterior, according to the posterior density here. So we want to maximize the posterior, and maximizing the posterior is equivalent to, and now we've taken the negative logarithm, which is why we like this exponential formulation here. We're going to compute the minimizer of this expression here. Okay, and there is an algorithm. This is an unfortunate name. It was named by a former student and collaborator, and I felt like I should use it. I probably would name it differently now. Iterative alternating sequential algorithm. So we have to solve this minimization problem. And we notice there's the fact that we can essentially separate the function that we want to minimize into a part that depends on z and the parts that depends on theta. So phase one, I fix theta, and I update z. I compute z by minimizing this expression here, which now I'm writing in matrix terms as 1/2 b minus a pseudo inverse of L times z. I take the norm of this square, and now that summation that I had, the glue summation, can be expressed as 1/2 times the norm of the d theta to the negative 1/2 times z, where d theta is a matrix, is a diagonal matrix which has thetas on the diagonal. One per entry there. And now we have z in the range of L. So this is a, so to speak, constrained linear least squares problem to solve. This is where most of the time is spent by my computer when I do the calculation, because this can be large. Then, once I've computed the new value of z, I update it, I use it here, and I go to phase two. And phase two is to minimize the portion of the objective function to minimize with respect to theta. So this is the expression that I need to minimize. And what I do is I write down the plain first order optimality condition, which is a necessary condition. It has to be satisfied. And it turns out that if I take the gamma distribution, I can actually come up with a solution in closed form. Remember that not any theta will do here. The thetas also have to be positive. So mathematically, you can come up with positive and negative. We only choose the positive because the mathematical solution also has to agree with the fact that this is related to a modeling of a variance here. So this is a very easy nonlinear system that has either a closed form or close to a solution here. Now, that was where the probability, the second portion here is where we used the probabilistic modeling, but now everything has become equations. Probability has done its job, and it's kind of like put to rest for now. Okay, now a little more. We mathematicians like to reduce problems to standard form, so let's look at the part, right, that we're penalizing here. So I'm going to call this L theta, and I'm making a change of variables here. So I'm introducing this new variable xi, which is L theta times x, and now I'm going back. X is the pseudo-inverse of L theta times xi. This is the diagonal matrix that I have. If I make this change of variables everywhere, and I look at what I need to solve in phase one, what I need to solve in phase one is what is called the Tikhonov regularization problem in standard form, or if you will, penalized least square here, where the difference between this problem here and classical Tikhonov is that I don't have any parameter. The parameter, well, is not really true, but the Tikhonov regularization parameter has been absorbed in this matrix here, L theta, or in the d to the negative 1/2 matrix here. But formally, this looks very simple and straightforward. And when we're solving this, we are only computing things in the 2 norm. So we're staying in the 2 norm, and we can resort to solvers for fairly standard problems. After having used this for about 7-8 years, very successfully, every time people would ask me, do you have a convergence? Do you have a proof that there is a convergence? Is there a unique solution? Is the algorithm convergent? And it turns out that after banging our head and quite a bit of analysis, virtuosity here, we were actually able to show that if we have a gamma distribution, which is, why I always start with r equals to 1, then the algorithm, the algorithm converges. The functional that we're minimizing is strictly convex, and in addition, we know what it converges to in the limit with, we are pushing one of these parameters to a limiting value here. Essentially, what we are computing is a solution which is in the limit, the solution that we would get if we were penalizing in the 1 norm. So we're going back to the L1 magic, but without ever changing norm. We only think Euclidean norm. So, and you can see that this is the solution. This is the closed form solution for the update that I was talking about. And then there is a little bit more. I mean, coming to talk in Pisa about linear algebra humbles me quite a bit, so I have to make sure that, I do things right. I've known Dario too long. Feel fully comfortable. Let's look at this. We have the solution here for Tikhonov. So we want to compute the solution to this minimization problem. So xi is the argument that minimizes this norm here. Now, the solution of this problem also solves, and I'm not saying numerically, mathematically, I can write it as the solution of the normal equation, these normal equations here. Now, alternatively, one could actually look at a problem, I call it the adjoint problem, and which in the case in which I'm looking at underdetermined problem is a lot smaller. So right now we're making a consideration of size. If I'm thinking about, if you think about this problem here, this problem can be very, very large. But if I have few data points, if I have few equations, this problem here is small, much smaller, and by luck it might even fit in memory, and I may be able to solve it directly in one step here. So I take the solution of this problem here, unique solution, and these are square non-singular matrices, and it turns out that after I've computed the solution of this problem, if I multiply by the transpose here, then what I get is automatically the solution of the Tikhonov normal equation. So these are normal equations. These are fake normal equations in the sense that they look like normal equations except that they're not, because here I have a B and there is no matrix multiplying this. So this is a simple observation which has made a lot of difference in very large problems here. And this is the proof. It's a very simple proof here. So, solution of phase 1, what's the best way to solve phase 1? If the matrix is available and my computer is large enough, then I can solve, let's say, the adjoint problem, the lower complexity problem, and then multiply by the transpose and get the solution that I want with the solution of a small problem and one matrix vector problem. If the matrix is not available in closed form, either my computer is not powerful enough, it doesn't fit, then I can solve the linear system via trivial subspace. I can use the Lanczos bidiagonalization. I can use the conjugate gradient, a conjugate gradient for least squares variant, and continue. And another problem that has to be addressed is that we have all of these formalism, but then they become real problems when one needs to compute it, because every time we iterate, so we update Z, we update theta, we go back, update Z again. When I get ready to update Z, well, theta here has changed because I have a new value of the variances. So what I need to do is I actually need to compute this pseudo-inverse at every iteration. And I can do it, and there are different ways to do it. For example, one can do it using the QR factorization. Turns out the QR factorization will slow things down quite a bit when the problem becomes large. This becomes the real bottleneck. So there are ways of applying it, and I'm actually looking forward to learning more about randomized linear algebra to address this problem. Because right now, I think the people have done a lot of progress in randomized algorithm for the QR. So, and I'm going to skip this. So let's just recap a second. So at every iteration, our algorithm, let's say, probability inspired or probability rooted algorithm defines and solves a Tikhonov problem of this type, which can then be put in a standard form. Then the matrix, so if I'm thinking about the matrix that on the diagonal, the D to the negative 1/2, so 1 over theta 1, 1 over theta 2, 1 over theta n, this acts as a regularization operator, as a penalty operation, but it's a penalty operation that acts differently, if you wish, weighs differently every component of Z. So in Tikhonov regularization, you have one parameter and one operator. One parameter has to address all of the needs. In this case here, the algorithm learns which components of Z wants to go to 0, which components of Z want to increase, and adjusts the penalty by tuning the variances, and all of this is encoded in the matrix d theta. So one can think of this as being a variant of Tikhonov regularization, and where we actually can update via a nonlinear step, probability justified way, let's say, the weights. So the weights change every time theta is updated. The calculation of L theta via QR factorization may be too costly. This part has to be addressed better. So this is just, we're starting to look at this. The Tikhonov adjoint formulation, something that it took me, I guess, 20 years to remember that I had written about it before I started using it. It's actually great at reducing the computational complexity. And then, again, iterative method, Lantos process, actually makes the method suitable for very large problems here. And now, what one can do is, one can actually go back and say, well, what if I want to do, can I use probability to update Tikhonov simplex? And the answer is yes. You can think that, by the way, I promised a block sparsity. I didn't talk about block sparsity. What you can do is you can actually take blocks of entries of X and have them move together. So instead of wanting sparsity in the entries, you can say that you only want a few of the blocks to be allowed to be, let's say, different from 0, and most of the blocks to be 0. So you can play, let's say, this block partitioning game here. And if one goes ahead and compares and looks at a bridge between Tikhonov, classical Tikhonov regularization with Morozov discrepancy principle and this, let's say, Bayesian inversion, or let's say probabilistic inversion, as I like to call it these days, then one can actually think that when Morozov discrepancy principle chooses a regularization parameter alpha based on the condition that the error that you make in matching the data D with the solution computed in correspondence of the parameter alpha should be about of the order of the expected error in the data. So you don't want to fit to the noise. That's what people say. Don't fit to the noise. You stop before you do that. So, this is the Tikhonov principle here. In our probabilistic setting, we don't have an alpha. We have these variances that are updated, and we keep going until the variances no longer settle, they no longer change, and then we can compute the corresponding parameter, if you want to put it in the classical Tikhonov framework, by taking the square root of theta and dividing the sigma, which is the standard deviation. You see that the noise level by it. Okay. And now I'm going to show some pictures. We finish with some pictures here. This is a numerical differentiation problem solved as an inverse problem. And what I'm showing here is, again, this Tikhonov meets Bayes, meaning that we're doing Tikhonov using this Bayesian framework to find the parameter. So this is the data, little noise, medium noise, big noise. Okay? And this is the Tikhonov, the solution, Tikhonov solution with, determined with Morozov discrepancy principle. I've actually done it 10,000 times, just to have, you know, a sense of what's going on over a sample. And this is Tikhonov done with this, let's say, with this Bayesian framework. And what seems to be is that, this was a referee who asked for this, so I have to thank the anonymous referee for giving us the chance. This seems to be less, let's say, more consistent, less variability. And this is the selection of the regularization parameter. There is clearly a power law when we're selecting it we're selecting it with probabilistically, and this is with the classical Tikhonov. So there is more consistency and actually less work in general here. Sparsity. So an example of sparsity, this is an X-ray, a fun beam tomography here. We had 15 views with 300 rays per projection here. We had finite elements, we had the triangular mesh, piecewise linear basis functions with about 4,000 nodes here. And we had this, so this is the forward matrix. And we look at the edges here because we want to describe sparsity. Sparsity in the sense that we want to describe that we expect to see a landscape that is mostly zero, and there are a few blobs which stand out. Think that you're looking for maybe a tumor or an inclusion somewhere. So right now, the sparsity is not in the entries, is not in the node. The sparsity is, if you wish, in the increment, in where the function increases. So we have this sparsifying operator here, essentially, which gives us the edges, which is about 12,000, which means that the matrix, our matrix, has 1,500 rows and about 12,000 columns here. And we computed it without, in different ways. And this is how we got the solution. So this is the first solution here. So what is happening here is, at the end of the first iteration, again, and what I'm showing is x, which is like from the sparse z. It seems to learn that around here there isn't much happening, and neither there is in the yellow spots, but at the edges, maybe there is something going on. So, the second iteration, it's already better. It has cleaned the background, and it's pretty uniform, above and below. Third iteration, fourth iteration, fifth, and sixth iteration. And that's pretty much it. So this is looking at the unknown, and this is the variances. And now, if you look at the variances here, you see that already at the end of the first iteration, when we update the theta, there is some indication that, let's say in phase 2, the system has learned that the action is around these edges here, and then maybe there is something happening in the background. The second time is just more secure, it's more clear that there isn't much happening other than at the edges, and it keeps refining this until it converges to this solution here. So if you're looking at this, you can almost see that this acts almost in this case as an edge detection, because the way in which we are expressing our sparsity is a sparsity in the increment. Right now, I'm working with a student from geology, joint PhD in math and geology, and he's looking at landslides. And we're trying to estimate the height of the landslide as it moves. And he's using a variant of this applied to the PDE, governing the equations. And when we are visualizing the theta, we were surprised, but what the theta was giving was giving pretty much the front along which the slide was moving, which was, something that we hadn't thought about it, but it made sense, given the application. So, that's it. Thank you very much for following.
for the very nice presentation. Other questions?
In many applications, the matrix A derives from, say, the point spread function, say in imaging, in image restoration, and therefore the matrix has specific structures. Besides sparsity, say it's a band matrix or block band or say tuplets or something like that. Can you exploit this structure in order to accelerate the execution?
We do. We swear by.
How do you write that?
I have it. Yeah. Yes, we do. We try to use everything that we have learned about structure matrices, everything that we also have learned about, differentiation. So we still do, operations by hand, so that zeros are entered as zeros and not as finite differences. And yes, when we have banded matrices, when we have matrices with particular structure, since the main engine here, where all the fuel goes, is into often multiplying, when the problem is really large, in making matrix vector multiplication with a matrix A, the faster that can be done, the more efficient. So, in particular, the first time when the first time here, learning this from the data usually requires more sweeps of the iteration. So, whether the matrix is used in a smart or dumb way will be felt in the wall clock time.
Are there other questions? Okay, if not, we thank the speaker again. Coffee break upstairs in the first floor. Not also that there will be an interview uploaded on the YouTube channel of the department. Our speaker agreed to answer our questions.